Hello and welcome to video number 2 of the A1 series. In today's video, I am looking at derived units, in particular force and energy. I'm looking at scalar versus vector quantities, explaining the differences and giving some examples. And then we're going to look at some basic stuff, distance time graphs, very important but quite basic, and then speed time graphs. Please enjoy the video. Okay, hi, welcome back. This is video number 2 of what will hopefully become a very long series. In this video, I hope to go through some more basic physics before we start on the hard stuff. Last time, we talked about base units and base quantities, and I told you there were 7 base quantities, each with their correct base unit. And I said not to worry about candelas, at least with 6. Today, we're going to be looking at some derived units and derived quantities. I already shared with you 2 from last time, if you remember. One of them was speed, and the other one was density, which was kilograms per cubic meter. You have got to learn by heart 15 of these, something like that, about 15 of these, and you are to know that they are derived, and you're supposed to know what they're from. And in fact, interestingly, of course, if you look at the units for density, it's just told you what to do. To work out density, you take kilograms and you divide it by the cube of the meters. That's it. So, are there any more that we really need to bring up this early on? Well, yes, there are. Speed, density. I think it's time to bring in force. Now, we know that force, the units of force, are newtons, N. But a newton is not a base unit, it is derived. We're going to do all of Newton's laws in detail, but there's one that you should already know, which is force equals mass times acceleration. If you don't know that from like year 9, year 10, or year 11, then you probably missed something. Force is mass times acceleration. Well, mass is in kilograms, and acceleration is the change in speed with time, and the units of acceleration are ms to the minus 2. So the units of force, a newton, can be written as kilogram meters s to the minus 2. Do we have to know this? Yes, you do. And you also know, we'll cover this later, that the work done when you push something is the force you push it by multiplied by the distance you push it over. The force is in newtons and the distance is in meters. So if this is force and I multiply it by distance, m, the result will be kg m squared s to the minus 2. And whenever you see that, you know you're looking at work done, also known as energy, and therefore the unit that we can use, instead of writing all of that, we can write J for joule, named after James Joule. Joule being the derived unit for the derived quantity of energy stroke work done. Okay, so the other thing, besides from knowing if something is a base quantity with its base unit, or is a derived quantity with a derived unit, you also have to know if something is scalar or vector. Something like mass is called a scalar quantity because a scalar quantity has only magnitude. It basically has a single number and its unit, in this case 15 kilograms, and it has only magnitude. It's a scalar quantity. Force, for example. Force is most definitely not a scalar quantity. It is a vector quantity. And a definition of a vector quantity is one that has magnitude plus direction. I don't like that definition. I prefer this definition of a vector quantity. If you represent it, could you do it with an arrow? You can represent a force with an arrow, and the length of the arrow represents the amount of force, its magnitude, and the direction tells you, obviously, the direction. In the book that we are going to be following for this whole series of videos, because this is the new 2023 edition of the Physics IBDP. I'm assuming that most of the students watching me right now have got this book with them. If you haven't and you're not doing DP, that's fine. We can do some A-level stuff. But if you're doing DP, you'll have read this book already with your teacher, and there's already stuff in here about base and vector quantities. And it says, I'm quoting for you from page 10. As an example, consider the amount of money in a bank account. A positive amount means that you are in credit, whereas a negative amount means that you are in debt and owe the bank money. Although the balance of the account can have a negative quantity, money itself is still a scalar quantity. I would agree with that. However, the bit they missed is that the amount of money in your bank account is simply a number on a number line and cannot be represented using an arrow. If it could be represented using an arrow, where the direction of the arrow represents its direction, then it would be a vector quantity, but it's not. They also make the point that you can have scalar quantities that are negative. I would agree. So, for example, an amount of money could be a scalar quantity because it's on the number line, does not have a direction. However, there is something I must talk about, and that is speed. Okay, so speed, the units of speed are meters per second. Now, I have always argued in my teaching of physics that there's no such thing as a negative speed, and I stick with that now. Because if you are an object moving around, the speed is simply how much distance you cover per unit time, and it has no idea where you're going or what direction you're in. And so to talk about, say, if I'm a dot and I don't have a front or a back and I'm just moving around at 2 meters per second, it makes no sense to talk about -2 because there is no backwards for me. I'm just a dot. I'm just a point object moving around. So I would say other scientists and teachers will disagree with me. But my argument is that speed would be written as 2 meters per second. If you write it as +2 meters per second, it's just wrong because you're now, with the plus in there, you're basically giving it a direction in a particular orientation. And this is no longer, that is no longer speed. It is now, because it has direction, velocity. And I would argue that if you say the speed is -2 meters per second, I would argue that is not a speed. I would argue that that is a velocity because you've put that minus sign on it. The book says that there can be scalar quantities with negative signs. I would agree. However, I would make the case of the speed that does not apply. The speed is only ever, it's not even positive. It's just, whatever you call that, an absolute number, a number without a sign on it. So we need to talk about speed and velocity. Speed is simply the speed. It's simply the amount of distance you travel divided by the time taken. Now, technically, that would be called average speed and has no reference to the direction you're going. Velocity is speed in a particular direction and can be shown, obviously, as an arrow. And there's another velocity arrow. Maybe that's going at 3 meters per second in that direction. Velocity is a vector quantity. Now, in this particular case, you could tell them apart because speed would be written as 2 meters per second, and velocity would be written as +2 meters per second or -2 meters per second. But that's a bit dodgy looking at that difference there. The actual units themselves, meters per second, are the same. And that's really, really confusing because you've got two different quantities, speed and velocity, that have exactly the same units. And yet one is a scalar and one is a vector. Well, I'm sorry, tough. We just have to live with that and work around it. That's the way it is. So velocity, the units of velocity are meters per second, and the rate of change of velocity is called acceleration. And you should know that the units of acceleration are ms to the -2. Interestingly, there is something called the rate of change of acceleration, which has the wonderful word jerk. And the units of jerk are ms to the -3, which is the rate of change of acceleration with time, but we're not going to have that in our course. Okay, so moving on. This is the stuff that you've probably done, what about year 9, year 10, maybe, what will be that, year 8, year 9? Distance time graphs. You've done it in physics and you've done it in maths, but we have to do it again now before we can move on. A distance time graph has time along one axis and distance along the other axis. And it basically tells you the story. So let's do a story, a nice easy one. Here's somebody's afternoon. They set off from home and for 1 hour they walk and they arrive at someone's home, let's make that 4 kilometers away. And they then have a little rest for 1 hour, don't go anywhere. And then they go and see their friend who is quite a long way away. Let's say, oh yeah, he's 12 kilometers away. Let's do that. Right, here we go. There we go. So he goes to his friends and then he stays there. And then he gets on the back of a motorbike and he comes back very quickly. And he arrives back 4.5 hours after he left. Now, hopefully you've seen all this stuff before, but let's just go through it. On a distance time graph, the gradient of the line tells you how quickly he's moving. When you were first told this, you were probably saying that was the speed. We can use speed or velocity. With this graph, it really doesn't matter. And I know because he travelled 4 kilometers in 1 hour, I know that during this time period, he must have been travelling at 4 kilometers per hour. The fact that it's fairly steep tells me he's moving, and the fact that it's a completely straight line, here's the important thing, the straight line tells me that the speed is constant. So a straight line on a distance time graph means a constant speed stroke velocity, but we're not going to talk about velocity right now. A constant speed. That was a constant speed. That was a constant speed. In this case, 0. And that was a constant speed. If we want to know the speed when he went from his friend's house, A, call this arriving at A and then arriving at B, the speed of his journey from leaving A to arriving at B was he went up by 8 kilometers and he went across by 1 hour. 8 divided by 1 is 8 kilometers per hour. So his speed during his time was 8 kilometers per hour. So question for you, how quickly or at what speed did he travel home? Well, the time he was travelling was half an hour. And the distance he travelled was all the way home 12 kilometres. 12 kilometres divided by half is the same as multiplying by 2. So he was doing 24 kilometres per hour on the back of someone's scooter on the way back. What do you need to know about distance time graphs? Because they're really important. Number one mistake. Students don't read it. They think it's another thing, which we're going to come to shortly, which is a speed time graph or a velocity time graph. You have to read it. Does it say distance? Yes. Distance time graph. All it's telling you is what is happening to his position with time. A straight line means constant speed. If it's a horizontal line, it means he is stationary. The steeper the line, the faster he is travelling. But you could argue it doesn't really matter. In this case, it's going up, which means he's like going away. So, key question. What does the area under that graph represent? Area. This would be 4 times 1. That'd be 4. Times a half, because it's a triangle. So the area of that graph is 2 something, isn't it? Because it's 4 high, 1 across, and it's half a box. So that'd be 2. 2 what? And the answer is, if you look at the units, that's kilometers multiplied by hours. The answer is 2 kilometer hours. What is the meaning of 2 kilometer hours? That doesn't mean anything. So the final thing you have to realize is that the area under the graph on a distance time graph is meaningless. It has no meaning. because it would be, in this case, kilometre hours. There's such thing as a kilometre hour. Any questions on distance time graphs? Excellent. The other type of graph is the speed time graph. You know it's a speed time graph or a velocity time graph because it says speed stroke velocity on this side and it has time along the bottom. And they look rather like distance time graphs, but they ain't. So let's do one here. Okay, so here we have a speed time graph. This is somebody on a motorbike, perhaps. Along the bottom, we have time in seconds, 10, 20, 30, 40, 50, 60. Outside, we have his speed. He starts off doing no speed, 0. He sets off, and after 20 seconds, he is doing 5 meters per second. This graph, because it's a speed time graph, is telling you how his speed is changing with time. And when your speed changes with time, in this case, it's going faster, you are accelerating. And the gradient of the line is not telling you how fast you're going, as it did before. It's telling you how much your speed is changing. So in this case, here's the key idea. The gradient of the line, whether it's steep or shallow or flat, tells you the acceleration. And you can work out the acceleration by, on the graph, getting a ruler and drawing a triangle. And if the question is, let's call this point A on the graph, and the question is, what was their acceleration from time 0 until point A? And so what would you do? The change in speed is plus 5 meters per second, and the time taken was 20 seconds. 5 divided by 20 is a quarter. So the answer is 0.25 ms to the minus 2. That is the answer. The acceleration during this first 20 seconds is 0.25 meters per second. What was the acceleration during the time from 20 to 30? My graph's rubbish, by the way. That's just the way it is. So what was the acceleration there? The change in speed was 5. At this time, it only took 10 seconds. 5 divided by 10 is a half. So here the acceleration is 0.5. What was the acceleration between 30 seconds and 50 seconds? Well, the line is flat. It's not moving. So you know the line's not moving, which means the speed is constant. The speed is constant. Acceleration is 0. Acceleration is not changing. Speed is constant. Acceleration is 0. And what about the last bit? So we're doing this, I think that's meant to be 50 over here. So let's call it from 50 to 60. There we go. 10 seconds along the bottom. They came back. They slowed down by 10 meters per second. So their change in speed is minus 10 meters per second divided by the time taken, which is 10. And that's minus 1 ms to the minus 2. That's basically what you have to do. Now, this is obviously pre-IBDP stuff. This is stuff that you should already know. If you don't know this stuff, you have got to go back and have another look. I'm going to give you another question in a minute. Okay, so let's do another speed time graph. Here's time in seconds. And 10. I'll try to make it half decent today. A train. And this is, I'll do speed out here. It's the speed of a train. And it's in meters per second. A train leaves the station here at time 0 and accelerates over 20 seconds. Let's do it, 20 seconds. And then levels out. And it carries on at a constant speed from 20 seconds to 50 seconds. And then it slows down and stops. So they're going to ask you loads of questions. I need to put some numbers on here for it to make sense. So I'm going to put one number on there. We're going to keep it simple. that's going to be 10 meters per second. Three questions, or the two major questions they're going to ask you. What was the acceleration during this part of the journey? What was the acceleration during the middle part of the journey? And what was the acceleration for the last part of the journey? Acceleration is change in speed for the time period divided by the time. You know that the acceleration is constant because the line's straight. In all the work we do, the acceleration for a particular time period will be constant, because if it's constant, we can use our simple maths for working things out. If the lines are curvy, then without doing very, very difficult maths, we can't work out things like areas under the graph. Acceleration here. Do you agree that the change in speed is from 0 to 10? So change in speed plus 10 meters per second. And we divide that for how long it took. How long did it take? 20 seconds. So the answer is plus 0.5 ms to a minus 2. What was the acceleration here? From 20 seconds to 50 seconds, it was travelling at a constant 10 meters per second. How do you know? Because the line's flat. So the acceleration here is 0 ms to the minus 2. What about the acceleration for the last 30 seconds, from 50 to 80? The change in speed is minus 10, and the time it took, 30 seconds. And that works out at minus a third, minus 0.33 ms to the minus 2 in that time period. Any questions? Does that sound reasonable? So you work out the acceleration by simply taking the gradient of the line. Now, what we're actually doing here is maths. We're actually working out the gradient of a line by taking the rise and dividing by the run. So we've worked out the acceleration, 0.5, 0, minus 0.33. And you know, just by looking at the graph, that you know the value of the acceleration there is less than that, because that line is steeper than that line. Not by much. That line is steeper going up than that line is coming down. I think you would agree. So the next question is this. How far did the train travel from leaving the station to stopping 80 seconds later? And this is where, I know most of you know this, but we need to go over it. The area under the graph represents the distance travelled. Now, the proper word for that is displacement. Displacement is the distance travelled from a starting point to an end point in a straight line. Let's just call it displacement or distance travelled on this graph. How do we work it out? Well, look, the easiest one is the middle bit. Do you agree that between 20 and 50 seconds, that is a time period of 30 seconds, that you were doing a constant 10 meters per second? What does 10 meters per second mean? It means you're going 10 meters every second. Well, if you do that for 30 seconds, you'll end up going, will you not, 10 times 30, which is 300 meters. Area under the graph can be determined by multiplying the time by the height of, in this case, a box. And because it's a box, it's a square, and therefore all we have to do is 10 times 30. The distance travelled by the train when it was travelling at a constant speed between 20 seconds and 50 seconds was 300 meters, because it's 10 times 30. But what about here at the beginning? Now, I'm not a maths teacher and I'm not into maths. So the way I do it is to say, well, look, do you agree that if I draw a little dotty line there, that's a box? And if that's a box and I draw a triangle from one corner of the box to the other corner of the box, by definition, I've cut it in half. So if I work out the area of the box and then halve it, I'll get the area of that triangle, won't I? And you've probably learned half base times height. So what is the area of this triangle? That's 20, the base is 20, the height is 10, times a half. Because 20 times 10 is that big box. We don't want the big box, we want half the box times a half. 20 times 10 times a half is 100 meters. So that represents 100 meters. So maybe you could have a go at the last triangle. The height of the triangle is 10. The width of the triangle is 30. And because it's a triangle and not a box, it comes about half, and that is 150 meters. So what is the total distance travelled by the train? 100 plus 300 plus 150, 550 meters. And that basically is all you need to know about speed-time graphs. Next time, we're going to develop speed-time graphs to then come up with these equations of motion that you're all so familiar with, or maybe you haven't been introduced to them yet. But we're going to go through that graphically to show you where the Suvat equations come from. Have you found that useful? See you next time.